Okay, I think we can start. Welcome back, everyone. Let me introduce our first speaker of today, Tomáš Bučko. Tomáš Bučko is Associate Professor at the University of Bratislava. He has contributed to VASP for more than 16 years now. As he is interested in catalysis, he's really the pioneer of all the molecular dynamics features in VASP. With his work, he made VASP attractive to a whole new community. For the next 1 hour and 15 minutes, he will give an introduction to molecular dynamics. Tomáš, please go ahead.
Thank you, Marie-Therese. Good morning, good afternoon, and good evening, whatever fits you. Welcome to our first lecture on ab initio molecular dynamics implemented in VASP. This is the overview of the lecture. Actually, the first lecture is intended more for beginners to give you really idea what molecular dynamics is about and what are the main ingredients of standard straightforward molecular dynamics algorithm. Okay, so this is the overview of the lecture. I will start by motivation, trying to explain you at which circumstances you should consider running molecular dynamics. And then we'll talk about some basics, some numerical integration of equations of motion, thermostats and barostats, measurement in molecular dynamics, and good practices. In the second lecture, after this one, I will talk a little bit about more advanced molecular dynamics, or MD, techniques aimed at calculations of challenging property, which is free energy of activation and free energy differences between stable states. Right, so the first question, what is molecular dynamics for, can be answered right at the beginning, right? And I hope you will still keep listening to me after that, after I answer this. Yeah, so you should consider it whenever you want to make realistic predictions of measurable quantities, right? That's because experimental measurements are always done or almost always done as measurements over enormous number of configurations and also over finite time. In quantum mechanical calculations, typically we deal with individual structures. So in order to be able to make realistic predictions, we need some bridge. We need some bridging theory, which basically links world of microstates of quantum mechanics with measurable quantities, world of some macroscopic properties, let's say. Now, if you think of it, so in experiment they measure order of 10 to 23 configurations in a single measurement. Fortunately, macroscopic quantities usually do not depend on fine details of those configurations, right? It's our everyday experience that basically the macroscopic properties are rather insensitive to initial conditions and fine details like exact atomic positions, exact atomic velocities at a given time. Take measurement of boiling temperature of water, for instance, right? So the outcome of experiment will not change when you repeat the experiment afresh by filling the teapot again and heating up. By refilling the teapot, you basically reset, or you redefine initial positions of water, and you redefine its initial velocities. This is completely different setting than it was in your previous measurement. Yet, when you measure boiling temperature, it will be probably the same number, right? So rather macroscopic properties don't depend directly on every single detail, on fine details of structure. Rather, they depend on it in some kind of averaged way. Okay, so that's the idea behind statistical mechanics. And essential concept here is that of statistical ensemble. That's collection of system that is described by same type of interactions, microscopic interactions, and sharing common macroscopic properties. And these common macroscopic properties, like number of particles, N, volume, V, and total energy, E, for instance, or number of particles, volume, and temperature. Okay, so this is what we use to label the ensembles. Okay, so having defined ensemble, then an observable is expressed as some kind of weighted average. Okay, so this is this example of such an observable expression in canonical ensemble. So here the integrals are taken over momenta of atoms, their positions. O of P and Q, that's phase space function linked with the observable. H is Hamiltonian, Kb Boltzmann constant, the temperature. Q appearing here, that's canonical partition function in this case, and loosely speaking, that measures number of, or is proportional to number of accessible states. And M, that's the prefactor, which first makes partition function dimensionless, and it also takes care of, ensures that that particles of the same type are indistinguishable. Okay, now you might say, well, I'm ab initio practitioner, and I don't run molecular dynamics, and I'm still predicting physical properties, and I think I'm doing quite well, right? So how about that? Do I really need molecular dynamics? Now, clearly, so let's think of it a little bit. So, what do you do when you just predict the physical property just on basis of some individual configurations, be it, say, potential energy minimum obtained in relaxation, right? So what you actually do is you replace this equation by this approximate expression where the ensemble average is replaced just by one single number. Okay, so this is phase space function obtained for a single configuration. Okay, at which circumstances is something like that reasonable? When can you hope that this gives you some reasonable answer? Yeah, so compare those two, and it's clear that this can only happen when the Boltzmann factor, this one, associated with this configuration is so large that it absolutely overweights the weights associated with all other ensemble members, right? Sometimes it is the case, but very often not. Yeah? So we have to be very careful about it, and we have to think very carefully whether or not static approach could give us reasonable results. To show you how serious this problem could be, I chose this example from my research. What you see here, that's a simple ionic crystal, scandium trifluoride, crystallizing in a cubic system. Here, it consists of octahedra, centers of which are occupied by scandium atoms, and corners of which are occupied by fluorine atoms. Okay, so now let's imagine that we are interested in prediction of bulk modulus for that compound. Bulk modulus, that's inverse of compressibility. That's quantity, thermodynamic quantity, that basically tells you how difficult it is to reduce volume of system by applying external isotropic external pressure, right? And bulk modulus is inverse of that. Now, most straightforward route to calculation of bulk modulus in static calculations is basically to perform series of relaxations with fixed volume, okay, and plotting total potential energy versus volume curve, okay. Now such a curve then can be fit by a suitable equation of state, like Monaghan equation of state, and then bulk modulus is basically one of fitting parameter. So this procedure works pretty well with the functional that I'm using here. That's PBE. It works pretty well for the class of materials scandium trifluoride belongs to. That's class of ionic materials. Yeah. So here you have some selection of ionic materials, and you see the comparison of PBE results of bulk modulus versus experiment. I mean, this performance is pretty decent. But when I apply this procedure to my system of interest, So I observed the following. I was quite disappointed to see that predicted bulk modulus 97 gigapascal was like 60% greater than the experimental value, right? Now, of course, the first thing to be to be blamed would be DFT, right? So PBE is known to perform not particularly well for certain class of systems. This is kind of Hall of Fame of failures of PBE. You see a couple of systems where, I mean, PBE works really terribly poorly, right? It's really terrible performance. Look at that. But yeah, this class of, but for this class of materials, we understand why the performance of semi-local functional was that bad. These are all van der Waals systems, and PBE simply doesn't describe long-range dispersion interactions correctly. So we understand why it fails here. But how about scandium trifluoride? I mean, this is material from this class. We don't expect it to fail so badly, right? So in what follows, I'm going to show you that DFT is not to be blamed in this case. So what you see here, that's the perfectly symmetric structure as it comes from static relaxations on one hand, and also as reported from X-ray diffraction experiment. But remember, in X-ray diffraction experiment, what they really do, they average over many structures, right? This is perfect symmetric structure, and you see here that scandium and fluorine atoms are perfectly arranged in lines and arrows when you look from the top, right? But in reality, when you admit thermal motion of atoms, well, you don't expect to find such a structure in reality, right? This kind of perfect arrangement is extremely unlikely, right? So when you let the system evolve and freeze it at any arbitrary moment for a while and look at the structure, it's more likely to look like this rather than like that, right? So you see that, I mean, there is significant deformation due to thermal motion of atoms. And this is exactly a fact that leads to strong softening of the structure. Let me explain the mechanism of softening, how this works. Yeah, so this is a fragment of the structure that I just showed you. These are two scandium atoms, and fluorine atom is just in the middle, right? Now, when we compress the structure, since scandium distance is just one cell parameter, right? So when we compress structure, we basically shift scandium atoms close together. And when we preserve symmetry, if we insist on having a fluorine atom still in the middle of scandium-scandium connection, then we necessarily reduce scandium-fluorine bond. But this is a chemical bond, and shrinking chemical bond costs energy. That's the reason why we see this steep increase in energy in compression region of our energy versus volume curve. But now when we allow for thermal motions of atoms, we know that it's quite unlikely to find this kind of structure, and especially, I mean, all structures to be arranged like that. Rather, it's more likely to find it somewhere in off-center position like this. And now when it is located here, so you can push scandium atoms closer together without really affecting scandium-fluorine distance significantly. Okay, so when you consider these kind of deformations, rhomboidal deformations, then you significantly stabilize system, making the EV curve in compression region much flatter. And bulk modulus is proportional to second derivative, to curvature of energy versus volume curve close to minimum. So making curve flatter also mean making bulk modulus smaller, softening the structure. Yeah, all these effects are naturally taken into account in the method I'm going to talk about today. It's molecular dynamics, that statistical mechanics method, which basically takes thermal motions of atoms into account. And bulk modulus can be computed from molecular dynamics directly from volume fluctuations in isothermal isobaric ensemble. Okay, so in this plot, I compare experimental results from bulk modulus with our previous static result. You see how far away it is from experimental reference. And here are our molecular dynamics results for different temperatures. You see, we got pretty close to the right answer. Okay, so the central idea behind the key idea behind molecular dynamics is ergodic hypothesis, which postulates that the ensemble averages and temporal averages are equivalent. Okay, so this is formally expressed here, but in words, it only means that you can equally well compute an observable by averaging the phase space function over many configurations frozen in time, or alternatively, you can pick one or few systems, let it evolve in time, and just average over time. Okay, that's equivalent. And this second way of doing averages is exactly used in molecular dynamics. We do temporal averages. So in order to do so, we need to evolve system in time, right? So VASP implements the version of method that is called ab initio molecular dynamics. Here, despite the name, we integrate classical equations of motion. Okay, so which might be derived in Hamiltonian mechanics from Hamiltonian. Here are the equations of motion, and in ab initio variant of the method, the forces are computed from first principles by solving Schrödinger equations, so usually at DFT level if you are using VASP. Now, so the word ab initio here just comes from the fact that electronic degrees of freedom are treated quantum mechanically. Nevertheless, nuclear quantum effects are completely neglected. That's the limitation of method. So things like 0-point vibrations, tunneling effects, tunneling or isotope effects are simply not involved, are not described by the method. The method is therefore inherently unsuitable for low temperature predictions, like say below 100 K, where these effects simply cannot be neglected. They are important. Now we are solving equations of motion in computer, right? So we need to use some kind of discretized form. Okay, so this is example of discretization of equations of motion, which upon some rearrangement give us basically integration scheme. Okay, so this is particularly simple but effective integration scheme called leapfrog algorithm that we also have in VASP, and it works as follows, right? So for the current time step, you compute forces, right, and use them to update velocities. Right, so you update previous velocities from the previous step, generate new velocities, and then you use these updated velocities to propagate positions. You generate positions for the next time step. Okay, so this is the point where quantum mechanical calculation comes in. You need to compute forces for the new time step, and you repeat this procedure over and over until you reach the desired simulation time. Now, of course, this procedure has to be initialized somehow. You need to start somewhere. You need some initial velocities and initial positions. So just like in all other kinds of simulations, initial positions are provided by user via the postcard file, and velocities. Yeah, this depends. This depends on the type of simulations you are doing, right? So if you are just continuing previous MD simulation, you can use basically velocities that are already recorded in Concar file. If you start from scratch, then you might want a program to generate set of initial velocities for you. If you decide to do so, then this is default option also. Then the initial atomic velocities are drawn at random from Maxwell-Boltzmann distribution given here, and also shown graphically here for different temperatures. Now, important ingredient here in the integration scheme is the time step and especially its size, right? So this has to be defined by user, that's parameter potim, and it must be chosen very carefully because a too large step, because a too large step does not allow for a correct sampling of high frequency modes and can, in the worst case, even cause numerical troubles like, SCF convergence issues. And too small step, on the other hand, results in inefficient sampling, right? So you just propagate a system in time, but since you are generating time correlated data, you really don't improve statistics, right? So you want to use as large time step as possible while maintaining good stability of your SCF calculations and having stable integration of equations of motion. Now, as a rule of thumb, time step should be set to be like factor 10 to 200 times smaller than the period of oscillation of fastest degree of freedom of your system. Okay, so I have example here. So for instance, if we compare simulation of one extreme case, hydrogen molecule, system A, and diamond in silicon phase, system B. So then basically the ratio between the time steps that you should use for those two simulations should correspond to ratio of their periods of oscillations. This is given by inverse ratios of their respective frequencies, and this gives you like factor 8. Okay, so the time step used for simulation of heavy atoms should be typically much larger than time step used for simulations of light atoms. But what you do when you have when your system contains both light and heavy atoms, right? So how to choose the time step? Yeah, of course, the light atoms decide, but there is also one trick of trade you might consider to use. So instead of reducing your time step, making sampling of, making motion of or propagation of heavy atoms basically slow or ineffective. So instead of that, you can also manipulate the mass of atoms. Yeah, so you can consider to increase mass of light atom, and you can do so without worrying about statistics. So if you are interested in static quantity, position dependent quantity, you can safely do this because one can easily show that that kind of physical property, position dependent property, is independent of mass in classical mechanics. So this is quick proof. I do this only for canonical ensemble. This is an observable in canonical ensemble. Here we factor out all terms that depend on mass. They're always associated with momenta, right? These terms are completely independent of mass, so you can put them. You can basically separate these two integrals. And since you have basically the same term in numerator and denominator, you can simply cancel them out. So you get result which is really independent of mass. Okay, so this is one thing you can consider to do in simulation. Another useful diagnostics tool or tool to help you to optimize time step is basically checking the energy conservation. So the molecular dynamics based on classical equations of motion as we discussed them up to now. Okay, so it's easy to show that for Hamiltonian system like that, the total energy is a constant of motion. Okay, just take time derivative of Hamiltonian, use a chain rule for that. For dotted quantities, use Hamiltonian equations. Okay, you get this. These two terms simply cancel, and you see that time derivative of Hamiltonian is 0. Therefore, energy doesn't change. That doesn't change in time. Simple proof. And providing the cell parameters of our system were not treated as dynamical variables. The straightforward molecular dynamics based on that generates NVE, that is microcanonical ensemble. And indeed, energy conservation in microcanonical ensemble is useful tool for optimizing time steps. So what you can do really is basically perform tests with different possible setting and check the energy conservation. So let's discuss it a little bit. So what you see here is time evolution of total energy in microcanonical ensemble molecular dynamics simulation performed using 2 different time steps, right? So, and you see that the energy is not perfectly conserved. Actually, we see short time scale oscillations. That's just consequence of discretization of equations of motion. But the important thing is that there is no significant long range trend here. Okay, so this is correct behavior, right? So when we reduce time step, we also reduce magnitude of oscillations. Nevertheless, oscillations are still there. But if you see significant long time scale energy drifts, like on this example here, then you know that something is very wrong. Okay, and the 2 suspects I would mention here are either noisy forces, right, or too large integration step. So you should check one of those 2. Okay. Now, well, if you run molecular dynamics to make experimentally relevant predictions, right? So then you realize that, well, the real experiments are only rarely realized under NVE conditions, so with fixed total energy. So instead of energy, it's more convenient to fix temperature, right? And instead of volumes, very often we fix pressure. So how about that? What can we do? How can we change the algorithm? How can we adapt the algorithm so that we can produce other than microcanonical ensembles? So just like in real laboratory experiments, in order to maintain temperature, maintain pressure, we need to use some proper devices, right? So in laboratory, temperature is maintained by using heat bath with heat capacity significantly greater than the heat capacity of sample. So this is it. So whatever happens in the flask where you have your sample doesn't affect temperature of heat bath, right? Well, what we really want to do in molecular dynamics is basically simulate the sample. We worry about what's inside, and we don't worry that much about details of heat bath. That's why we can use pretty crude physical models to represent heat bath. And yeah, this could be either deterministic or stochastic models. Here, I would like to make short presentation of thermostats that are presently available in VASP. So first one is deterministic Nose-Hoover thermostat. The original Nose method is formulated. So equations of motion are derived from extended Hamiltonian, written here, where in addition to physical degrees of freedom, momenta, and positions, so 2 extra degrees of freedom are introduced, so position and momenta of fictitious degrees of freedom associated with heat bath. Okay, so now you see that in this Hamiltonian, well, there is one parameter. This is mass-like parameter, ms, associated with this fictitious degree of freedom. And this is something that you as user have to provide before starting the simulation. This is basically the only adjustable parameter of thermostat. Now, how to choose it? Okay, so one can show that the frequency of fictitious degree of freedom S depends on this adjustable parameter according to this equation. So this pseudo mass, it doesn't really have dimension of mass. It's I think energy over square time, I guess. It's not really mass unit. Nevertheless, well, you can estimate for the given mass, you can estimate expected frequency. And now for optimal coupling of your heat bath degree of freedom with your system, ideally you would like to have the fictitious degree of freedom to oscillate at about the same frequency as is the dominant characteristic, let's say characteristic frequency of your real system. Okay, since the thermostat is deterministic, it can also be used. So not only for generating ensemble averages, let's say ensembles, but also for calculation of time correlation functions. And this thermostat is available only within canonical ensemble. Next thermostat I would like to talk about is example of stochastic method. That's Anderson thermostat. And it's conceptually very simple. It works as follows. So we loop over all atoms in our system, okay? And for each atom, I, we replace with likelihood pi its velocity, okay? And in that case, we replace its actual velocity by the velocity drawn at random from Maxwell-Boltzmann distribution again. So in some sense, this procedure mimics random collisions of the system with heat bath particles. Okay, so this is schematically shown how energy evolves in simulation where temperature is controlled by Anderson thermostat. So basically, between collisions, the system evolves as in microcanonical simulation, so with conserved or quasi-conserved energy. And every collision then basically resets velocity, therefore changes the constant of motion, right? So this causes kind of discontinuous changes, right? And then we again get to another microcanonical regime. This is another collision and so on. So clearly, every such collision rapidly destroys any correlation in the motion of atoms. And that's the reason why Anderson thermostat and I think stochastic thermostats in general are intrinsically unsuitable for calculations of time correlation functions. The collision probability pi, that's something that has to be provided by user. That's the adjustable parameter of thermostat. Clearly, when you set pi to 0, okay, so there are no collisions whatsoever, and you just stay in microcanonical regime. So with pi equals 0, you can just perform microcanonical simulation. Okay, so how to adjust pi? Well, I think a rule of thumb is that, well, it should be large enough to have good control of temperature over a reasonable time scale, say few picoseconds you would like to achieve. Your average temperature you should see that it converges, it is close to desired temperature. Okay, so it should be large enough for that, but it should not be too large, because then basically in extreme case where pi is 1, so it's every time basically the velocities, actual velocities are reset. So basically then you basically switch off effect of physical forces and your motion is completely random then, right? So the larger pi, so more fraction, larger fraction of physical configurations you might generate, and the convergence of a physical property of interest might be slower. And this is last thermostat. I'm going to talk about Langevin thermostat. This is a non-Hamiltonian system. Equations of motion based on the Langevin thermostat are modified compared to classical equations or Hamiltonian equations of motion. So the difference is that for the force, we express two extra terms. First one is the friction force. Okay, gamma is friction coefficient, pi is its velocity, or momentum of atom I. And so the friction force, and we also add random force. This is drawn from random normal distribution with 0 mean and variance that is proportional to friction coefficient gamma, temperature, and mass of atom. Okay, so once again, friction coefficient gamma is the parameter that has to be set by user. If you set gamma to 0, clearly you make this and also this term vanish. So once again, you revert back to microcanonical ensemble. Right, so the greater gamma, the more aggressive thermostating. And once again, you want to have gamma large enough to have efficient thermostating, small enough to have your system driven by physical rather than stochastic forces. Okay, so now I would like to say a word or two about what we call instantaneous temperature. So when you run molecular dynamics, you see in output, after completing every single molecular dynamics step, you see in output some kind of temperature. That's exactly this instantaneous temperature. It's quotation marks used here because this is not really well-defined physical property. This is kind of auxiliary property, and actually, if you look into literature, there are several different ways how to define instantaneous temperature. The definition that we use is based on equipartition principle. So what you see here is just twice kinetic energy divided by 3n, n is number of atoms in the system. And clearly, with this definition, if you average over instantaneous temperature over sufficiently long time, you should converge to physical temperature, right? So this is what is printed in the output. And I'm mentioning that because it's important to realize that this quantity is subject to fluctuations. It can be shown that these fluctuations are inversely proportional to root square of number of atoms in the system and also heat capacity of the system. And these fluctuations are inevitable for finite system, evidently, right? So in this plot here, I compare time evolution of instantaneous temperature for two simulations of identical system, but yeah, this is just one unit cell with 6 atoms, and this is 2 by 2 by 2 supercell of the same system, right? So I just increased the number of atoms here. So you see that for a small system, according to this formula, fluctuations are much larger than for larger system as expected. And you see that these are temperature, yeah, it's this black line here, it's 300 K. And you see that the fluctuations are sometimes pretty large. Yeah, so they exceed, so that the instantaneous temperature might temporarily exceed like 700 K easily, and can also reach, I mean, very low temperature on this side here. Okay, so once again, this is expected behavior. So you see something like that, especially if you have small system, don't be surprised that your temperature, instantaneous temperature, is not identical at every single time step to what you defined in the input file. Okay, so much about temperature. So now let's talk about external pressure. Of course, it's trivial fact that when you impose external pressure, so your system responds by changing volume, right? So that also implies that in the simulation with controlled external pressure, we must treat cell parameters as dynamical variables. So to this end, VASP implements Parinel-Raman method. Corresponding equations of motion can be derived from this Lagrangian, which is defined in terms of fractional coordinates of atoms, S, and elements of lattice matrix, H, and associated velocities. So the first term here is its kinetic energy of atomic degrees of freedom. This is potential energy that depends on both positions and cell parameters. This is kinetic energy associated with lattice degrees of freedom, and this is external pressure contribution to total energy. This ensemble, well, equations of motion derived from this Lagrangian would generate NPH ensemble, where H is an enthalpy, that's internal energy plus P, volume term. Okay, so this is the conserved quantity in that ensemble. Now the method can be coupled with Langevin thermostat. We have to remember that, yeah, we have also extra lattice degrees of freedom. So you have to define friction coefficient for both atomic and lattice degrees of freedom separately. Okay, so when you do so, then you generate NPT ensemble. Now we know also from relaxations that well, whenever we change volume in a simulation, then Poulet stress becomes an issue, right? And in order to avoid it or eliminate its effect, we need to use much tighter electronic structure setting, typically higher plane wave cutoffs or denser grids than we use in constant volume simulations. So therefore, NPT molecular dynamics simulations are typically much more time consuming when performed at ab initio level than canonical NVT simulations. Now, adjustable parameter of barostat is W, which is mass associated with lattice degrees of freedom. This is purely fictitious parameter. It's hyperparameter of method, if you like, and it has no physical counterpart, and therefore it cannot affect for the physical property that you measure in your numerical experiment. Yeah, to show that, I basically follow here the same line of so same arguments as before when talking about mass dependence or mass independence of position dependent properties, right? So basically, once again, you express an observable, you separate that term that depends on W. It's only the one that is associated with lattice momenta, and you just cancel it out. Okay, so clearly an observable and NPT ensemble must be independent of mass, right? So hence we can set it up simply based on our computational convenience as we need, right? Andersen suggested that when the goal is to simulate dynamics of atoms, so not only static averages as we do, but also dynamics of atoms, velocity autocorrelations functions and things like that. So Andersen suggested to relate the period of volume fluctuations, okay, because this term actually controls this period of lattice cell parameters fluctuations. Okay, so Andersen suggested to relate this, equate this, relate this to time, that sound wave needs to travel through cell dimension. So sound wave of velocity VL travels to one cell dimension. Okay, so when you equate these two equations, so then you basically get this estimate of cell mass. So in my experience, this is typically large number. This is typically a few hundreds or even thousands of atomic units, depending on size of unit cell. But once again, we should keep in mind that W has no physical counterpart. It doesn't affect your physical properties or predictions of physical properties, but it does affect the efficiency and stability of your simulation, right? Yeah, so to examine this, I performed test. This is I did perform the test on my system strontium zirconium trisulfide containing 160 atoms in unit cell at high temperature 1500 K and at 0 pressure. And I performed simulations with identical settings except of W. In one simulation, I use extremely small value. In other one, extremely large value, 10,000 atomic mass units. You can see that, of course, the size of W affects the frequency of oscillations as expected. But when we compute the physical property, let's say bulk modulus again here, so we basically converge to results which are within statistical uncertainty identical in both cases. But we notice that the statistical uncertainty for the simulation with large mass is much greater than statistical uncertainty for that with small mass. That's because basically fluctuations were too slow, and making this sampling much less efficient. We would need much longer simulation to improve upon that. Okay, many useful quantities such as internal energy, various geometric parameters, many physical properties, work function, probability distribution functions, and things like that. So can be expressed as temporal averages directly. Okay. Now, as indicated here, free energy is important exception, and we will talk about this important exception in our second lecture, which is all about free energy, by the way. Well, since such averages are meant to represent equilibrium properties, these results should be stationary, should not change in time. And the practical consequence of that is that the piece of data that we use in the post-processing, in processing to extract averages, must be trendless. Must be trendless. Okay, so we must basically select that period of that part of data that we generated that is really trendless, and only that can be used in relevant predictions. Of course, in any case, the initial part of trajectory is almost always affected by initial conditions, right? And this initial period, sometimes called equilibration, should be discarded from the data before computing averages. Now, well, how to identify that? How to identify this initial period? Yeah, well, one can do this visually, as people often do. Okay, so you just look at your data and you see you have some trend here, so we'll cut that, right? But I think it's always better to eliminate human intervention as much as possible. I think it's always a good idea to do so. So it's better to have some more systematic, some numerical tool, right? Well, Schiffer and Valance in their very good paper proposed to use a set of statistical tests to identify basically equilibration period and production period. And one important test is Mann-Kendall test, statistical test, which is designed specifically to reveal trend in data. Okay, it's very useful exactly in this context. So this is how it works. So the test is based on evaluation of statistics of the number I, okay, which is the number of increasing pairs of data points. Okay, so you take your data and you basically count how many pairs you can construct, pairs of data you can construct in such a way, okay, pairs xj, xk in such a way that xk is greater than xj, while index k is greater than index j, right? So if your data are trendless, perfectly trendless, so you expect the number of increasing points would be the same as the number of decreasing points, right? And those together would give you total number of pairs that you have in the system. Therefore, you can define this parameter S, statistic S, which is basically twice I, okay, and minus the number of pairs. So once again, if your data are perfectly trendless, twice I would be exactly the same as number of pairs of your data points. So, and the result would be 0, right? S would vanish perfectly. So in this statistical test, the null hypothesis is that there is no trend in data. This is subject to test, and it is rejected if S deviates statistically significantly from 0. Okay, so it's conceptually very simple. So in practice, what we do, we start with raw data as we generated them in molecular dynamics, and run the test. If it is not passed, then we remove some small chunk of data from the initial period. Okay, so say initial 1,000 data points, and repeat the test. And we keep on repeating the test and removing small piece of data until the Mann-Kendall test is passed. So this is how it works. So these are my raw data. Don't be confused that different parts are colored differently. This is just one series of data. Okay, and clearly, I already used this as example. Clearly, the initial part here up to, I don't know, here is strongly affected by initial conditions. So my initial value of A was too small compared to typical value, right? So I clearly have some trend here. So that's why this whole data set did not pass the test. So I had to remove whole red part until I got this, which passed the test, right? And Mann-Kendall test not only helps you to to identify trends to identify the equilibration period, but also helps you to identify some unpleasant surprises in your simulation. Okay, so like this one, this is example of data which would never pass Mann-Kendall tests. What happened here was that I was close to coexistence of two stable phases, which basically shifted there and back from one phase to the other during the simulation, causing discontinuous change. Every time phase transition occurred, there was discontinuous change of my measured quantity. And of course, that would be a mistake to make average over all that. Of course, we want to treat every phase separately, right? Okay, so this is a little bit silly example, but I need to go through it because we need this also for our further discussion on advanced molecular dynamics techniques. So this is an example of an observable, a special kind of observable, which is histogram approximation to probability distribution function for some arbitrary quantity A. Okay, so in plain words, A, so that probability density, that's probability to find the value of quantity A, which falls into interval between AI and AI plus some increment. Okay, so formally, probability density can be expressed as expectation, so an observable based on Dirac's delta function. Okay, and by ergodic hypothesis, it can be expressed like that. So what we do in practice is that we monitor the function associated with observable A in our molecular dynamics, right? Then we basically define the interval on which the A fluctuates, so minimum and maximal value, right? So this is definition interval of that function. And then we split that interval into smaller subintervals, and we just count the number of occurrences A falls into each subinterval. This way we get distribution function, which upon normalization, when you divide it by number of measurements or number of points, gives you approximation, histogram approximation to probability density. Now, if A is a geometric parameter, such as bond length, bonding angle, and what have you, right? So VASP now allows you to quite conveniently monitor that parameter or any set of such parameters by defining it in file icons, and then you can see computed value in the output. Okay. Now suppose that we have already identified and eliminated the equilibration period, and we already made our prediction for our quantity of interest. Okay. Now the question is, how reliable is our prediction? In other words, was our simulation long enough? Do we need to run longer simulation to improve results? Okay, or is the quality of our prediction already satisfactory? Okay, so let's discuss that a little bit. So in order to avoid confusion, I will start a little bit. Discussing first the quantity that does not reflect statistical uncertainty. That's standard deviation. That standard deviation that basically expresses how broad distribution is. So to explain, what you see on this plot, that's orange, that's histogram approximation to probability density of my quantity V, and black curve, that's the fit, Gaussian fit to it, right? And sigma, that's just so standard deviation that reflects the width. And now, so now I argue that basically this quantity doesn't reflect uncertainty, but rather basically tells you something about physics behind. Let me give you an example. I better explain it on example. Spark modules that we already discussed. I already told you that it can be expressed in terms of volume fluctuations in NPT ensemble. Now, if we compare this defining formula with with standard deviation expression, you see that it is nothing but KBT, average volume, divided by variance, that's the square of standard deviation, right? So now single out sigma, and you nicely, you can express it like this, and you see that here you have constant temperature, average volume, which is a physical property, it's your estimated volume, and physical property, right? So clearly this does not reflect, this is something that you cannot minimize, but by running longer and longer and longer simulation, because the physical quantity will not change if everything is well converged, right? This is a list. I mean, here are a few other examples of quantities that can be also expressed as fluctuations. This is isochoric heat capacity, which is expressed as via fluctuations, or fluctuations of total energy in canonical ensemble. Isobaric heat capacity, that's the same for enthalpy, or thermal expansion coefficient, which can be expressed as cross correlation between volume and enthalpy, for instance. So what we really are interested in, instead of width of distribution, which cannot be affected much, is basically the uncertainty with which we determine mean, right? Mean is our estimate of physical property. So in this example, that would be uncertainty associated with position of Gaussian, right? And this is reflected by the property called standard error. It is related to standard deviation via this formula here. And clearly this quantity reduces, this is something you can reduce with the number of independent measurements. Okay, so now I emphasize that capital N in definition of standard error, there's number of independent measurements. But the problem is that in molecular dynamics, it is not what we do, what we generate independent measurements. Instead, the data points we generate are time correlated, sometimes heavily. And it would be therefore a big mistake to simply identify N with the number of MD steps. Our prediction, our estimation of uncertainty would be simply too optimistic, right? Let me give you again an example. Is a measurement of bonding angle of water molecule in gas phase. That's alpha here, right? So I measured that in two different simulations with low and high temperature. I got these average values, and basically to one decimal place, basically zero vanishing uncertainties, which doesn't look correct, because especially when I look at the distribution for high temperature, I don't think the position of this flatter Gaussian is determined with without any doubt. Okay, with its perfect accuracy, right? So evidently that estimate must be too optimistic. So what can we do about that? So how can we take care of time averages? There is an elegant way how to do that. That's block averaging. And this is how it works. So you start with your original data. These are basically, this is what you sample in molecular dynamics. You have L time steps, let's say, and you compute your standard error, right? And then you replace pair of data points by their average. So A1 and A2 is average to give A1 prime, and you do so for every subsequent pair. Okay, in this way, you reduce number of data points by factor 2, but at the same time, you also increase kind of effective distance between two data points. Remember, these two were separated just by one time step, and the separation between those two is, I mean, effective separation would be like 2 time steps, right? So, and by that, you also remove a part of correlation, right? And then you repeat this procedure. So again, you block, you replace pairs of data by average, and once again you compute standard error, and you do so many times, and in the end you display standard error as function of block size, and this is a typical. This is how it typically looks like if everything is correct. So initially, as you start blocking, you observe steep increase This is where you basically eliminate most effectively time correlation. And after this steep increase, we have plateau. This is basically a region where your prediction is more or less independent of the size of block size, and this is also your best estimation of standard error. Okay, so this is what I did for my low and high temperature, and I guess I correctly predicted here that the standard error for higher temperature is significantly larger than standard error for low temperature, as I would say, just looking at these two distributions. Okay, so this brings me to very final part of this presentation, right? I would like to give you some examples of application of these simple of these basic molecular dynamics approaches in my own research. So first example, that's adsorption of small molecules in zeolite called shabazite. Zeolites are aluminosilicates with open structures, and they are industrially important. They are used as catalysts and molecular sieves. Okay, so people, experimentalists and theoreticians quite intensively study their properties. And one type of experiment is measurement of adsorption properties and adsorption enthalpies of small molecules, from which one can learn about the locations and concentrations of active sites, and about the nature of their interactions with various chemical functional groups, let's say. Okay, so well, therefore since we had set of good quality experimental data for adsorption energies for some small molecules in shabazite, so we decided to test our methodology, how close we get to experimental reference data. Okay, so we were up to predict adsorption enthalpy, which can be computed in numerical experiments as follows. So this term here is average potential energy for the system of substrate and adsorbate. This is basically this one, substrate, zeolite, and adsorbate small molecule, minus average potential energy of clean substrate and average potential energy of adsorbate in the gas phase. So if you think of that, this is basically internal energy of adsorption. To make it to convert it to adsorption, heat of adsorption, enthalpy of adsorption, we have to consider the PV term. Well, we did so for adsorbate. That's why we have this KBT term here, and we neglected that for these two terms. So for the terms for system containing substrate, because substrate is solid crystalline material, and it is very unlikely that PV would be affected significantly just by adsorption. So PV term is most likely to be cancelled in this subtraction, right? I think this is a very reasonable approximation. So we performed calculation.
The 10-minute reminder.
So 10 minutes?
Yes, that's until the break. So there are 2 questions in the chat. If you have time to take them in the end.
All right, so 5 minutes.
But we can also.
Excellent.
Great. 5
minutes and I'm done. All right. Yeah, so I will accelerate a little bit. Okay, so we used a simple PBED2 level of theory, and these are predictions. You see that for most cases, we got fairly close to experimental reference, but well, there is some exception here where we don't have that good agreement. So clearly the problem here is basically the electronic structure level, the level of theory used to describe electronic structure. So to improve our results, we have to beyond this simple level of theory. We used RPA, which is state-of-the-art method, which is known to perform very well for van der Waals systems. And well, actually, to use RPA in connection with molecular dynamics is not very easy. RPA is very time consuming, and in the time the forces were not available at RPA level, but we were able to produce MD quality data for RPA using certain tricks to machine learning, which I'm going to talk about in my second lecture. Okay, so using RPA, we got fairly close to experimental reference data for every single system, and I think we reached chemical accuracy in all cases. Next story, that's phase transitions and characterization of melt of mineral cryolite, which is used as a solvent in famous Hall Héroult electrolytic process, which revolutionized aluminum production. Okay, so before 1893, I guess, yeah, I think, when this process was basically announced or invented, the price of aluminum was as high as the price of silver, right? So it was costly, but this process actually made it really cheap, and just after invention of the process, the price of aluminum was reduced by a factor 80. And that's why aluminum is now everywhere, right? Yeah, so there is some interest in characterization of melts. So to understand the relation between its properties in the whole Héroult process, etc. So that's why we investigated. We started from low temperature solid phase and made phase transitions over high temperature solid phase to liquid and characterized the melt liquid. Here I compare. So, we perform set of isobaric isothermal molecular dynamic simulations. Here I compare what we had for solid states with experiment. You see that experiment is very good. Yeah, so it's both qualitatively and quantitatively. Also, our prediction for transition temperatures is very good for solid to solid phase transition, not so good for solid to liquid transition, but we used only simple PB functional, so clearly there is room for improvement. Furthermore, having generated melt, we were able to characterize it. There is interest in basically distributions, prediction of distribution of this kind of particles, ALF clusters. We predicted many different things. For instance, average coordination number among other things. And here on this plot, and this is taken from publication of Machado and coworkers published after our prediction was made. This is experimental measurement, and you see our point is sitting exactly on experimentally measured point, which is always nice to see. And the final story here brings me back to scandium trifluoride, which we started with kind of at the beginning of this lecture. We studied it actually because this material shows very interesting, unusual property, a large negative thermal expansion. Most of materials expand when they are heated. This material shrinks, okay, over a wide range of temperatures, okay. And previous theoretical attempts to reproduce this phenomenon failed. They were based on static approaches, quasi-harmonic approximations, and things like that. So that's why we attacked the problem by using molecular dynamics in isobaric isothermal ensemble. We nicely reproduced correctly reproduced the negative thermal expansion plateau and positive thermal expansion at high temperatures. Besides that, we also were able to make predictions on more subtle things, like, for instance, scandium fluorine distance was predicted to increase even at temperature ranges where the overall structure shrinks, okay, which is a little bit counterintuitive. Nevertheless, this is our prediction, and these are experimental measurement published later. Okay, so I think that was it. And now I'm looking forward to your questions.
Great. Thanks a lot for this introduction, and thank you for taking some questions. So first off, how does the leapfrog algorithm treat energy conservation?
The
leapfrog
I'm not sure if
algorithm.
I really understand the question, because the thing is that the leapfrog algorithm just follows. This is just based on discretization, directly discretizing Hamilton's equations of motion, which inherently conserve total energy, right? So discretized version of Hamilton's equations of motion. This is leapfrog algorithm. That's one way of discretizing them. So inherently, they should also conserve the total energy, at least within certain accuracy, right? I'm not sure what is meant by treat energy conservation. Well, in principle, in leapfrog algorithm, the smaller time step you choose, the closer, the tighter you conserve energy. So, well, for infinitesimally small step, I guess you would also get rid of these short timescale oscillations. Leapfrog algorithm does fairly well for large time scale energy conservation. So given how simple this algorithm is, I think it performs fairly well. Okay, but there is no special treatment of energy conservation. This is like the property of algorithm, which inherits from what it was derived from. This is my understanding of that.
Well, if the participant wants to voice out their question, if that didn't answer, then you can raise your hand, and then I can allow you to ask your question directly. But otherwise, I will go on to the next question for the NPT ensemble. How do I determine the value of Langevin gamma and P-mass?
Right. So starting from P-mass, this is what I try to discuss a little bit. So I will maybe switch on the slide.
Specifically, the system that this attendee is interested in would be iron carbon, if that helps to specify the answer. But I think a more general discussion would anyways be useful for everyone.
All right. Yes. Yeah. So, well, as I said, so I was trying to discuss the strategy to choose W. Unfortunately, I think at least some kind of trial error procedure is inevitable if you want to work effectively, I guess. Right? If you just want a safe setting, let's say, and you don't care so much about sampling efficiency, then simply use default for W, which is 1,000 atomic mass units. It's large value, which large enough for typical unit cell to lead to stable simulation. So W should not cause you any troubles. If you make it smaller, you can basically very likely you can converge faster. The quantity that you are up to could converge faster. But you should test it. Unfortunately, there is nothing better than really testing this in a series of short simulations and simply find some small value for which this while still maintaining stability of algorithm and stability of electronic structure calculations. So okay, so I use quite aggressive setting in my own calculations. So I set W to very small values. As small as possible, right? This is what I do. Once again, a conservative setting. If you don't want to see surprises, use large value. Use default 1,000, or simply use Anderson's criterion. Okay, this is also quite robust setting. And for Langevin gamma, that was the second question, right?
It was already sufficient answer for this participant. There was a reaction, so I think.
Okay.
Last question. How do you optimize or know the ideal number of configurations required for an NPT or an NBT run?
Yeah, simply by estimating the error, right? So this is what standard error is for. Okay, so in principle, you can, I mean, the rational procedure would really be, if you don't want to waste a second of your CPU time, you run relatively short sequences, like 1,000 steps. And after completing each sequence, you recompute your average and determine standard error. If it is smaller than threshold that you preset, then you stop. If not, produce another sequence and continue. This would be like rational way to. I never do so. I usually produce longer than, at least I try to produce longer trajectories than necessary. But well, in the end, it is my standard error estimate that decides whether my quantity of interest is well converged or not. And if it is well converged, there is no reason to run the longer simulations, right?
So a lot of testing. Okay,
a lot of testing, yeah, that's experimental.
Yeah. So let us take a break, and then we look forward to the next lecture from you. Thank you.
All right. See you.